Yeah, when, one thing we talked about on double integrals is if we do the double integral over a region D, just do the double integral of the function as one, and essentially what that gives you is that will give you the area of D. So it's another use, I guess you might say, of your integrals. Well, in polar coordinates, then, if it makes sense, to describe your area in terms of polar coordinates. You remember, like in remember doing the roses, those ones that had the loops in them, or that's one of the ones we'll do. So sometimes it makes sense to describe an area in polar as opposed to Cartesian. So in polar coordinates, what this means is what we saw was your double integral. So we can get that area in polar same way, but the conversion, remember, is the double integral. So first of all, so dA, remember what its conversion was. We're going to r's and thetas, but so it's d. We do the thetas first, and then the r's. Oh, no, dr to theta, sorry. But there were one extra. We have to add in one little thing there when we convert over to polar from Cartesian. That r dr. So it's the double integral of r dr d theta instead of just dA. And then of course, so we do the r's. So we've got a function. How do we? So h1 of theta is what r's to h2 of theta. Sometimes like two functions between r goes between. And then the thetas, we need to, of course, go from, I'm just going to use alpha and beta for the thetas. Okay. So it's, what we're basically going to do here is just revisit some Calc 2 areas that we did in polar coordinates. But we're going to use double integrals here. All right, so example 1 here. Find the area of one loop of r equals 4 sine 2 theta. So yeah, you might have to pull out the old calculator again and graph these again, figure those out again. But it turns out this in polar, so change your polar and 4 sine 2 theta. It's the 4-leaf rose, I think they called it, or something like that. All right, and so, I mean, those are supposed to be symmetrical. Excuse my drawing, but yeah, they want us to find the area of one loop here. And so the point we're making here is that call that area D. And so area D we can do by this formula here, this double integral, r dr d theta. So there's, I mean, in this case, your function will just be r there, but anyway, we just have to figure out our upper, lower limits. Yeah, so we start with the r's, so we know ultimately, we go to the R. So where do we go? What's our lower limit? Well, R just starts at the origin, so R is 0, and then goes out to the curve there. So that's pretty easy. So 0 to 4 sine 2 theta is what the R's limits are. And then the theta, okay, so now on the thetas, I'm going to have to think about it a little bit. I mean, we could probably guess, but sometimes you need to verify that your guess is correct there. All right, so theta, remember theta is the angles that we sweep out here. So theta, obviously we start at theta equals 0. So the question then, well, how much of an angle do we have to sweep out there to get it back? So the deal is I start at R equals 0, which is theta equals 0, and then I sweep it out. The question is, all right, so what do I need to sweep that out? Well, the note what I have here is that the theta starts at R equals 0, and then when I come back and sweep the whole loop out, again the R is 0, so I need the theta angles where R equals 0. And the way you get that is just set your R equals 0, 4 sine 2 theta equals 0, and so that'll tell you the angles in this particular case that we want. So so it's just sine of 2 theta equals 0, isn't it? And sine is 0 at the pi's, and so in this case the angle though is 2 theta, so 2 theta would either be 0 or pi, 2 pi. I mean, we go backwards too, but yeah, that probably verifies your first guess here, because then if you divide by 2, you get zeros and pi over 2, pi. That's where that equals 0, and then you have minus pi over 2 and so forth. So yeah, the 2 where we're talking about is 0 to pi over 2. Like I said, that's probably what you would guess, but verified it out there. Is that okay? Question or concern? Where I got that? Okay. All right, so now then it's just a matter of doing the double integral. Do the inside first, 0 to pi over 2. Doing the derivative integral with respect to r, so that would be 1/2 r squared. So then we're going 0 to 4 sine 2 theta. So plug that in. So that'd be 1/2 4 sine 2 theta squared minus, and plug in 0, you got 0. So half of 16 sine squared. So that'd be 8. So I'm going to do the integral of 8 sine squared 2 theta. Oh. Which brings another blast from the past here. How do we do sine squared integral? Remember the old double angle? So yeah, that sine squared, we changed that by the double angle identity. For sine of 2 theta, sine squared theta, we had sine squared theta, or sine squared x. I believe sine squared was 1/2 minus 1/2 cosine 2x. Remember, cosine squared was 1/2 plus 1/2 cosine 2x. So in this case, for x, I've got 2 theta, and so it would be 1/2 minus 1/2 cosine 4 theta. Because my x is 2 theta, and so 2 times 2 theta is what that would be. Been a while. Remember doing that though, hopefully. All right, so this would be 4 minus 4 cosine 4 theta. And so I didn't put my limits, but so now we're doing the integral with respect to theta, so that would be 4 theta, And here's a little, it's just a little u substitution, u equals 4 theta, du would be 4 d theta. Yeah, so that's just, so it'd be 4 cosine of u and then d over 4. So the 4s are actually going to cancel out. All I'm doing is cosine. So that is minus, antiderivatives, cosine is just sine u, but u is 4 theta. And then I'm going to evaluate that 0 to pi over 2. So 4 times pi over 2 minus sine of 4 times pi over 2 minus 0 minus sine of 0, so that's 0. So it's 2 pi minus sine of 2 pi, but the signs are nice, that's just 0. Lots of zeros, so it's just 2 pi. Anyway. Question or concern? All right, one other one we did, there's no further thoughts on that. Was the area between two curves, polar curves. All right, so let's find the area between r equals 3 plus 2 sine theta. Oh. So find the area inside, be specific here, it is between, but this is the way they'll phrase it. Find the area inside that one, but outside r equals 2. Something like that. So r equals 2 is a pretty easy one. Just a radius 2 circle. Then the r equals 3 plus 2 sine theta, that was a cardioid shape, if you recall us using that phrase, but I think it's vaguely something like that. And so I'm talking about this area right in here. Okay. But it sets up fairly nicely for a double integral. Okay? So that area I can do with this double integral. Call that, d, rd theta. Yeah, because works out pretty nicely here, because what I'm doing is my r goes from this one out to this one. So my lower limit is 2, and my outer limit would be 3 plus 2 sine theta. Yeah, because the r there, that's what r does. Okay. Now the thetas, so the thetas would range from this angle right here to this one right here. So how do I figure that out? Well, if you'll notice, that's where the two graphs intersect. So to get an equation to solve for that, you just set the two r's equal. 3 plus 2 sine theta equals 2. And subtract 3. 2 sine theta equals -1. So sine of theta equals -1/2. And so then you just have to figure out, well, what are my angles that give me sine is -1/2? The reference angle would be pi over 6, but I want it to be -1/2, and so I'm talking a quadrant, yeah, it's quadrant 4 and quadrant 3 angle. So what would that be? So the reference angle is pi over 6 know what I'm saying? But I need, that's, because sine of pi over 6 is 1/2. But I need it to be negative 1/2, so that's what I'm saying, it's gotta be a quadrant 4. Well, if I want to range from this theta over this, what quadrant 4 angle would that be? Reference angle is pi over 6. What angle would I start at? I'd probably want to start at, because I want to go this way, right? Negative pi over 6. See what I'm saying? Start at that quadrant 4 angle, which would be negative pi over 6, and then go to the quadrant 3 angle, which what would be that angle? Quadrant 3. So it'd be pi plus pi over 6, 7 pi over 6. So anyway, kind of figure that out that way. So that's my theta limits. And then just evaluate from there. So we do the r's first, so that's 1/2 r squared. And fortunately, we got to go between, one of the things isn't 0 this time, but yeah, so that's 1/2 3 plus 2 sine theta squared minus 1/2 2 squared, which is 4. So it's not too bad, but it's a little bit of work here. So it's 1/2. Oh, let's do this. 1/2 times 9 plus square that out. 6 would be 12 sine theta, and then 4 sine squared theta, and then times 1/2 that, so it'd be 9/2 plus 6 sine theta. 2 sine squared theta, and then we got the minus 2 there, which all that does is 4.5 minus, so it'll be 2.5, 5/2 plus 6 sine theta plus 2 sine squared theta. Yeah, the only hard part about that is this one again. You got to use the double angle again. Yeah, these two are going to be easy. The 2, so we have to do the 2 times 1/2 minus 1/2 cosine 2 theta. Make that change again. So that'll give us 5/2 plus 6 sine theta plus 1 minus cosine 2 theta. Good thing is that cancels those halves out, if you will. So, we should combine that. The only thing here to do this one, let's see, that would be 7/2. Yeah, this is easy, 7/2 theta, antiderivative. That's easy. Antiderivative sine is cosine, negative, right? Antiderivative sine is negative cosine. Yeah, and then the antiderivative of that, you just have to do a little substitution. Basically, you're going to divide by 1/2 here. Yeah, you have the integral of cosine of u. Then you got d over 2 or 1/2 times du. So that's just 1/2. So you got 7/2 theta minus 6 cosine theta minus 1/2, and sine of u, but u is 2 theta. So So once you get that, oh, notice I forgot to write my limits all the way down, but it's negative pi over 6 instead of pi over 6. So if we plug those in, 7/2 times 7 pi over 6 minus cosine 7 pi over 6, et cetera, et cetera. I get, because of the chase here, it's like a little time. I love the little answer. Do a little work. 11 squared times square root of 3 over 2 plus 14 pi over 3. Once we get all the things calculated there. Question or concern? Look okay? I mean, we didn't go all the way through it, but let's see. Oh.